Now, we talked about what happens when the contractors screw up. So those of you here yesterday, you're going to probably hear some of this again. What we like to do in our specifications, and obviously these anchor bolt locations become very critical. Boy, nothing's nastier than having to solve a problem of a 2-inch anchor bolt that's 3 inches off from where it's supposed to be. Not often are you going to be able to move the column, right? So you're either going to rip out that anchor rod or you're going to refabricate something to make it work. So the best solution is to not let it happen in the first place. How can you do that? Well, put in your specifications that the contractor use you may even want to say a registered surveyor. We've taken a lot of flack in our spec by saying that, and we've now used the term qualified field engineer. But the point is, in our pre-construction meetings, we pay attention to this and say, Mr. Contractor, who's going to be the guy surveying the anchor bolts to be sure they're in the right place? Because if you mess that up, that's a very expensive fix for you and me. So I try to think about this a little bit ahead of time. Use AISC recommended hole sizes in the base plates, which now have gotten fairly generous hole dimensions to allow for more tolerances. Just a quick side story, if this didn't come up yesterday, you should know about this. ACI, I believe it's standard 112, defines all the concrete tolerances for concrete construction. And in their tolerance, ACI tolerances, they define a tolerance for anchor bolt or anchor rod placement. ACI specifies the same tolerances within the AISC Code of Standard Practice. Guess what? They don't agree. They don't agree by a large amount. The AISC tolerances are much smaller. It's a big surprise, right? They're steel anchor rods. The concrete tolerances are much looser. Contractors love to pick up on this and say, my contract's based on placing those anchor rods by the ACI tolerances. I didn't pay any attention to the AISC Code of Standard Practice tolerances. So word to the wise, cover this in your specs and tell them anchor rods are to be placed according to the tolerances specified by the AISC Code of Standard Practice, not the ACI 112 or 114 standard, whichever one it is. Again, we also require in our specifications that they use templates, 2 layer templates, one at the top of the anchor rod where the nuts are, it sticks out of the ground, and another template at the bottom of the anchor rod, so that you don't get anchor rods that are at the right spacing, but then maybe do this. You got to have 2 templates. So hopefully, if the contractor gets the top tolerance is correct and the bottom tolerance is correct, you'll get the whole family of rods in the right place, and you got at least a chance. But the point is, you want to have them surveyed maybe even twice for critical situations so that you don't have to do a very expensive, time-consuming, and job-delaying field fix to solve that problem. The other available options, obviously, you can evaluate the need for the incorrectly located rods, and perhaps not all of them are required, and you can just cut some of them off and not even use them all. You can cut the rods and use epoxy anchors. That's expensive and painful, but you can drill holes deep into the concrete with long drill bits and fill it full of epoxy and develop an anchor rod that way. Make a larger hole and use plate washers. We've done that before. If it's only 1/4 of an inch off or 1/2 inch off, sometimes you can wallow out the hole in the base plate, make it come through, and then put a plate washer welded to the top of the base plate to get the hole back to its correct size. You may have to throw away the old base plate and fabricate a new one that matches the incorrectly placed anchor rods, if that's possible. Relocate the column on the base plate. That might work for a metal building or a warehouse where they can afford to move the column, but most architects frown upon the fact of the engineer asking to move the column. You can bend the rods into position. If they're only a little bit off, sometimes you can apply heat to the anchor rod and bend it over enough to make it fit through the hole. That works, of course, if you only have a small error. You can provide a design with ample length so that if the rod gets pushed down into the concrete, it's still long enough to put a nut on it. So we like to specify extra extensions on the anchor rod so that if the guy pushes them down 6 inches, they still work. If possible, do not use high-strength anchor rods. Use larger diameter rods that can be welded, because here's a situation where welding might come in handy. If you have to weld an extension onto the anchor rod or a sleeve. And of course, you can do that now in this new spec by specifying weldable grade 55, or of course A36 are weldable. Extend a short anchor rod by welding on a threaded extension. That's a possibility. Use a coupling nut to extend the rod. Cut the rods and use epoxy anchors, and these other solutions that we've kind of talked about. Okay, coming to the end here. Any questions about column bases? Yes, sir.
My question is about the shear friction at the column base plate.
Yes.
And in relation to the oversized holes that are typically to be provided based on the practice, how have you rationalized how the base behaves, particularly if there's very thick plate material for the base plate?
Very good question.
That's why I asked it.
Yeah, the way we have handled that is to specify post-grouting of the hole with a very high-strength grout so that you fill that contact space and then therefore validate the shear friction concept. That's the way we would do that. Any other questions? Okay, we're getting tired, huh? All right, we're getting close to the end here. I want to spend just a few minutes talking about steel trusses. Steel trusses is another one of those elements that you don't really learn a whole lot about in school. And so we do a lot of trusses, both in our long span building practice, but also in buildings where you have transfer trusses. Sometimes when you're spanning 150 feet, a plate girder doesn't work very well, and you get into a shallow truss. So we're going to talk about the various types and anatomy of trusses, strategies and geometry, member selection, connections, and some practical tips. Most of this is not anything very new to you. It's sort of obvious. A truss is nothing more than a form of a beam where you have shear and flexural stresses that you have to resist. The shear forces are taken by the diagonals and the posts. The posts, in this case, act in compression. These diagonals are acting in tension. And then the flexural stresses in this beam-type member are taken by chord forces, compression chord in the top chord, tension stress in the bottom chord. So the truss is nothing more than a form of a beam. Because it's a beam, you can draw a shear diagram and a moment diagram, and you can use the shear diagram to proportion the diagonals and the posts, and you can use the moment diagram to proportion the chords. Very simple concept of how a truss works. This is what we call the truss panel point, and the question that frequently comes up is, how do you proportion the panel points of the truss? What are some of the rules? Before we get into that, though, let's talk about the various kinds of trusses. And every single one of these you'll probably use sometime in your career if you work with architects who like to have all kinds of shaped roofs. So they're king post truss, which we've used a lot of, the fink truss, the scissors truss, the bowstring truss. And recently we did another one that we came to call the Brunel truss. A Brunel truss is a truss that basically acts like a catenary. The bottom chord is curved, just like the top of that bowstring. The top of the truss is also curved, just like that bowstring. The top takes compression. The bottom takes pure tension. The tension is constant along the span at the bottom. Compression is constant along the span at the top. And the only thing you need is posts between the tension catenary and the compression member at the top, at least theoretically under uniform load. It's a little more hairy if you have unbalanced loads, and there you start to develop shear in that truss, but that shear force is taken by the top and bottom chord. So a Brunel truss, the word Brunel came from a bridge engineer in London, or in England, in the UK, that designed a teardrop-shaped truss spanning across as a railroad bridge. And his name was I. Kingdom Brunel, so that's how the word Brunel truss came along. Anyway, there's all kinds of forms of trusses. They all basically have shear carrying elements and flexural carrying elements. Tension and compression for the flexural members, and then tensions and compressions for the diagonals and the posts. There's an optimum range of economy for a truss in proportion to its span. If the depth is too small, you have large chord forces, because basically the chord force is nothing more than the moment diagram divided by the depth of the truss. So M over D, if D is small, then M over D, which is the chord force, gets to be very large. If the truss gets too deep, you're kind of shooting yourself in the foot. You're reducing your chord forces, but now you're making your shear members much longer, and so you start spending all your material and all your money into the shear elements like the diagonals and the posts. So obviously there's an optimum range in there. And interestingly enough, if you ever do a cost parametric study on optimizing the depth of a truss, you find out that the cost curve is kind of flat. In other words, there's a range of depth in there where it really doesn't change very much. And that usually works out to be 1/10 to 1/12 the depth of the span. In other words, the depth of the truss is 1/10 to 1/12 of the span. If you make it 1/8, you're probably spending a little bit more money. If you make it 1/14, you're probably spending more money. But 10 to 12 is generally, for most trusses, kind of that economical range. Now, one of the things that we talked about earlier, structural steel costs, particularly in heavy truss construction, are more driven by the connection costs, not the member sizes and the costs. Heavy trusses, and I'm talking about trusses that are spanning 300 feet, carrying thousands of kips, all of the money in those trusses is primarily in the connections. So sometimes it pays to be more economical on the connection, spend a little bit more money on the members. The rule is to simplify the connection design and simplify the connections themselves to reduce connection costs. Connection weight in long span trusses can be as much as 30 or 35% of the weight of the whole truss. That's a lot. So these connections not only are expensive, they also can be pretty heavy with the gusset plates and the bolts and the stiffeners and the welds. Panel point spacing, primarily governed by the location of the loads that frame into the truss. Generally, when you design a truss, you want to keep bending off of the top chord or the bottom chord, because then the chord, instead of acting like a column with axial load only, it acts like a beam column. You put bending in that beam column and you're going to spend a lot more money. So generally you want to bring the loads into the truss at the panel points, even if you have to subdivide the panel points to make that happen. And I'll show you a picture of that in a minute. Try to avoid at all costs putting uniform loads on the top chords of trusses, because that's very expensive. Those already have heavy compression forces in it. Now you're adding big moments in there as well. You're going to make your truss a lot heavier and also make the connection more complicated. So panel points are generally dictated by the spacing of the members that frame into them. Keep your focus on the connection while selecting the member types. Many times I've seen engineers in our office design trusses. They sketch up what they think the truss wants to look like. They assume an orientation of the member. They form their computer model. They input the model, put the forces in, get the member sizes out. They think they're done. Then they go sketching up a connection detail, and they say, oh, wow, this doesn't look too good. If I'd only turned this member the other way, or if I'd only done this, or if I'd only done that, this connection would be a lot easier. guess what? The moral of that story is sketch up the connection first, then go do the analysis to proportion the member sizes. You'll find that you'll save yourself a lot of time at the end of the day if you conceptualize the connections first, then go in and proportion the truss and determine its member sizes. Generally, secondary moments, if you do have some secondary bending in the top chord of a truss, generally you can ignore that and design that truss as if it were pin connected at the ends of all the members, and design it only for the axial forces. Those secondary moments have been shown not to be significant in the ultimate load carrying capacity of the truss. So most trusses you design as pin connected members. If you want to design the top chord as continuous, you can certainly do that, but then you have to be consistent between your analysis and your design. If you're going to design that top chord as continuous, then you have to design the connection to be continuous and the forces from your analysis in the connection. You can't design the truss to be continuous chord and then ignore the moments that you get in the chord. You can't have your cake and eat it too. In other words, you've got to be consistent between your analysis and your design. And sometimes engineers don't do that. Connections are what it's all about when you talk about trusses and costs. The simplest kind of truss you can do is a double angle top chord and a double angle or single angle post and web members like you've shown here. We have a single gusset plate. The angles can either be shop welded or field bolted depending on the size of the truss. Remember, you can't ship a truss over the highway that's much deeper than about 13 feet, maybe as high as 16 feet if you get a special permit. So our rule is if we can make our truss 16 feet deep or less, we make all of our joints shop welded. Do all that welding in the shop, ship it out in one piece, then only use a bolted splice every 60 feet or 120 feet, depending on how long you want to ship it. If it's 20 feet or 24 feet, then you're pretty much stuck with field bolting the connections. You have the option of field welding the connections too, but we don't like to do heavy field welding out in the field unless you have an inspector there, because field welding is problematic in the sense that you're out in the wind and the rain and the elements, and sometimes the welding isn't so easy. So we like to do shop welding, field bolting whenever possible. Whenever you can, double angles or T sections. If you can, make the T's deep enough where the web members can bolt or weld directly to the T stem, that saves the cost of that extra gusset plate. So you might try that. The disadvantage to that is if you use a real slender deep T, you're going to get into that H over T problem that we talked about earlier, and you'll have to design that T as a slender compression element because it's going to have compression in it. So there's a trade-off there. If you get it too slender, you got to go into that slender member provisions of Chapter F. Sometimes instead of double angles, we've used double channels as top chord members. Again, keeping one single gusset plate if you can until the forces get too big. Then you may have to go to either a double gusset plate. I think what we're showing here is trusses made out of HSS members that architects tend to like, either pipes or tubes. Generally, if you can use one gusset plate that's welded to the cord and then slot the tube or the pipe in the field or in the shop and then weld it to the gusset plate around the perimeter, that's not too bad of a connection. Pipe trusses are oftentimes used with the same concept as we're showing here. This is the most expensive one. This is the one the architects always love, right? That's the one that's obviously the most expensive. These really aren't too bad. And I like pipes and closed sections for compression members in trusses because they have long unbraced lengths. You're going to quickly learn that the proportioning of trusses and the weight of members is often controlled by the amount of axial load you can carry for the given unbraced length. And you want as long of unbraced lengths as you can without sacrificing too much buckling capacity. In other words, to use the steel, you want to stress the steel up as high as you can toward the yield strength, but if you get the member too long, then you'll take that buckling resistance hit. So 2 members are great to get long unbraced lengths. Sometimes if you're shop welding a truss, you may want to do a shop weld like this with a wide flange turn with the web vertical. Field or shop cut all these members and weld them into place. Again, I might consider doing this only if the truss were 16 feet deep or less where you can ship it over the highway. Obviously, you'd never want to do this in the field. You'd be crazy to do a welded joint like that in the field. When you start getting big, heavy trusses, you may be stuck with double gusset plates, 1 on each side. This is the standard truss connection for W14 or W16 or W12 shapes. Use this cord with a web horizontal, a double gusset plate, 1 on each side with bolted flanges. This is probably the bread and butter truss connection. Sometimes you can get away with turning the web of the wide flange vertical, 1 single gusset plate with wide flange posts and diagonals that have the so-called claw angles bolted from the member onto the gusset plate. Fabricators tend to like this one as well because it's only 1 gusset plate, but unfortunately it only works for what I would call medium to lightly loaded trusses. If you get really heavily loaded trusses, this isn't going to work very well, and you're going to need 2 gusset plates like we have over here. That's why this is the standard for heavy trusses. So practical tips for truss designs, most of them we talked about. Always consider the connection design and the member selection design process first, not last. Engage the fabricator or erector in the design process. If you know who your fabricator is going to be, before you start the design, go have a meeting with them and say, hey, what is your shop practice? How do you like to do trusses? And you want to have the erector at the meeting. So get the prejudices of the fabricator or erector early on in the project if you can, so that you'll get the best bid price. Try to use bolted connections and limit welding to the shop only where possible. For repetitive trusses, consider grouping member sizes. Additional tonnage may be offset by the savings in detailing and fabrication. Document a detailed erection plan and assumptions made in your erection process. For long span roofs, some of the heaviest loads the roof will ever see are during construction, during erection. So the engineer should have a preconceived erection process in his mind that he shows on the drawings as a suggested erection procedure to the fabricator erector team. If he wants to come back with an alternate, obviously you can entertain that, but you ought to give him a way to do it that you know that works. Design and detail connections on the construction documents if possible. If not, clearly show the design forces, including all through forces for connections. Envelope of forces may not be sufficient for independent engineer to design the connections. That is, if you just give him the envelope of forces, what I call the maximum and minimums for every member, frame it into the joint without the transfer forces, he's going to have to make an assumption on what those transfer forces are that he can't get from statics by himself. And therefore, you're probably going to end up with a more conservative design. So don't think that just by giving him the envelope of forces for each member, you've done your job. You need to give him the through forces as well, or otherwise he'll probably come back to you and ask for them. Study the camber requirements and show the camber requirements on the truss construction document drawings. Don't wait till the shop drawing stage to do that. Bracing members from the computer analysis may not be proper when the tolerances are out of straightness or not considered in the analytical model. When we design a 300-foot span truss, we put an out of straightness in the design process to build in that P delta analysis so that we model the secondary forces more accurately and more correctly. You don't need to do that for normal buildings, but for long span construction, you ought to consider actually analyzing a model that's out of straightness, because it will end up being that way whether you like it or not. Consider using slip critical bolts and oversized holes to alleviate fit-up problems. I've seen it argued both ways. Some erectors say, yeah, we like slip critical bolts with oversized holes. Some fabricators say, no, that's too expensive. So again, you got to sit down with your fabricator erector team, let them fight it out, and then come to you with what they want to do. If not, you're going to be forced to make a decision, and I've always found it better to go with oversized holes and slip critical joints. And the reason is that will eliminate most of the time the need for field fixes or wallowing out holes in the field, which I don't like to do with long span trusses, obviously. For long spans, consider using higher strength material for reducing member sizes. We like to use grade 65 steel in our long span roof trusses because you generally can count on that higher yield strength in the design, and the cost of grade 65 material is anywhere from 0 to 3% more than grade 50. You almost get that extra strength for free. The only disadvantage is it has to come from overseas with Arcelor, what used to be trade our bed, and therefore there's a little bit of a shipping delay, a potential delay in the project. But if you mill order the steel, you probably have time to do it. I think you'll save some money using grade 65 steel in long span truss design. Okay, let me close this next section in just 5 or 10 minutes. We'll talk about computer modeling and verification. Before I get into that, though, any questions about trusses anybody would like to ask? Yes, sir. Yeah, the question was I familiar with the Miller Park collapse of the Big Blue, I think they called that crane? I'm generally familiar with what happened. I think it was a combination of things, but where's your question headed here? I think some of the expert witnesses involved in that case were wind tunnel people, actually. The two wind tunnel experts of North America served on opposing sides. And the story I got back, and it was finally settled out of court, but the primary cause was operating that crane out of the wind conditions that were acceptable. In other words, wind load played a major effect on that crane losing its load. Okay, how are we doing here? Yeah, no, this will go real fast here. Computer modeling and verification. We always, and I talked a lot about this earlier, always try to get the engineers to, number one, look at the deflected shape from the computer model and be sure that it makes sense. Go back and check the input data and be sure that it's consistent with the output data. How many times I've seen us design grade 50 steel on the contract documents only to see that it was 836 steel in the analysis, or vice versa. You want to put on the drawings what you used in the analysis. Obviously, doing some very simple checks of the computer model, looking at deflected shapes and mode shapes is one very powerful way to be sure your model is correct. Another way is to look at the force distribution in the members, the axial loads and the moments, look at the boundary conditions, do some quick hand calculations to be sure that the computer model is giving you an answer that comes reasonably close to your approximate back of the envelope statics check that you do. So just doing some simple things can help you check yourself in your complex computer model. I always tell the engineers also that these programs all have the capability to do a first order analysis, and then you can activate a P delta second order analysis as well. One of the most important things about that, always start out by doing a first order analysis, look at the deflected shape and the deflections, then turn on the second order effect and look at the analysis again. If the difference between the second order and the first order is more than about 10 or 15% in terms of forces and displacements, it ought to raise a flag in your mind that something's not right. If you run the first order analysis and everything looks great, and you run the second order analysis and it bombs, guess what? You got an instability somewhere. Either the model's wrong or you've got a system that isn't stable. So don't stop at the first order analysis, okay? The second order analysis is very critical to be sure you have a stable structure, But always compare the second order analysis to the first order analysis, and don't let the difference between them be very much. If it is, you may not have a stiff enough structure. If you turn on the first order analysis and you get a deflection of 10 inches, and you do a second order analysis and it's 20 inches, that means you got a P delta effect that's 100%, and that's way too much. You have a soft structure that's potentially unstable. So that's another trick to check in your model. Compare first order analysis and second order analysis. Always look at the boundary conditions. I'm going to let you peruse these in your own. Let me pick out one here. In a lot of our long span roof design, we sometimes use pot bearings where you want one end of a truss to slide or one end of a beam to slide. And that all works good, and the assumption you make in the model is that that's a frictionless surface and that there's no force buildup. Well, remember that you can't buy any kind of a frictionless roller or a Teflon pad or anything like that with less than about a 5% coefficient of friction. And so if you're pulling on a truss, for instance, with a pretty large axial force, you'll put 5% of the reaction as a horizontal load on that support before it will overcome the friction and actually slide. Now, that doesn't make a difference if you have a beam that has 10 kips on it. 5% of 10 kips is nothing. 5% of 5,000 kips on the top of a shear wall or a column is a lot of load. So you want to remember to always consider that so-called shear friction force, or that friction force, in your design. Many engineers forget to do that, and they end up with a support that cracks or additional lateral load that they didn't ever realize that they had. So that's what this one is all about. We talked about rotational stiffness at boundary conditions. I think one of the common mistakes I see in using these computer programs is unbraced lengths. If you don't tell the computer program what K is or what the unbraced length is, it usually will assume something. And usually it assumes the length of the member. And that may or may not be right. Sometimes it may be half the length of the member is the real unbraced length. Sometimes it's twice the unbraced length of the member, or the real length of the member. So if you be careful in your final check of the member size that the computer program used the correct unbraced length of all the members in your truss or your frame, whatever it is you're designing. We talked about consistent properties between what you design and what you show in the drawings. Member end releases should reflect the connection, fixity, or flexibility. Do not release moment at the end of a member and then provide a moment connection. In other words, my rule is you analyze what you design, design what you build. You got to close the loop there and be sure you're consistent throughout the design analysis and design and construction process. This talks about the diaphragm and the master-slave thing. I think we hit a lot of that stuff earlier. Loading, remember that you've got to consider eccentricity of wind load as well as eccentricity and seismic load. That's required by code these days. I think we've talked about most of this stuff here. So that's pretty much the end. It's 4:45, so I want to get you home on time. And before we break it up, though, I'll stay around for a little while if anybody has any questions. Any quick questions, be glad to take them now. Okay, have a safe trip.